Sand is discharged at A from a conveyor belt and falls onto the top of a stockpile at B. Knowing that the conveyor belt forms an angle 25 degrees with the horizontal, determine A, the speed v0 of the belt, and B, the radius of curvature of the trajectory described by the sand at point B. Okay, we'll focus on a single particle of sand as it just leaves the conveyor belt. Okay, we'll first try to find v0. Let's look at what we know. So there's no acceleration in the x direction, but there is an acceleration in the y direction due to gravity. That's negative 32.2 feet per second squared. Looking at the picture, we can also figure out that the initial x and y velocity of the sand. The belt discharges sand with a speed v0, so its initial x velocity is v0 cosine 25 degrees, and the initial y velocity is just v0 sine 25 degrees. Now we can write some equations of motion in the x and y direction. So the sand's x position is just the initial x velocity times t, and the sand's y position is just the initial y velocity times t plus 1/2 the acceleration times t squared. This is just kinematics. Replacing the velocities and accelerations with our knowns, we get these two equations that both contain v0. So we know at some moment in time the sand reaches point B. If we set the origin at A, that means its x position at B will be 30 feet and its y position will be negative 18 feet. And this will occur at some time TB. So now we have two equations and two unknowns. We can find an expression for TB by rearranging the equation on the left. And we can substitute that expression for TB into the equation on the right. Now we'll have one equation and one unknown. Now we can solve for v0, which turns out to be 23.5 feet per second. Plugging v0 back into the equation for TB, we find TB to be 1.409 seconds. So we're done with the first part. Now we need to find rho, the radius of curvature. We'll use this equation that says the normal acceleration is equal to the speed squared over the radius of curvature. So let's say here's an object moving along a red dotted line. It has an acceleration a, and there's some component of the acceleration that points with the path. That's the tangential acceleration. What we're interested in is the normal acceleration, which is the component of the acceleration that's perpendicular to the path. And rearranging that equation, we can get this explicit formula for the radius of curvature, which is simply the speed squared over the magnitude of the normal acceleration. So we'll go back to the things we know from before. The initial x velocity, initial y velocity, v0, and tb. We'll find the speed vb first. We can find the magnitude of its x and y velocity first. Its x velocity is simply the initial x velocity, because there's no acceleration, and its y velocity is the initial y velocity plus acceleration times time. Once again, we can use our knowns to get these equations. We'll find that the x velocity, plugging numbers in, is 21.3 feet per second, and the y velocity is negative 35.5 feet per second. Using Pythagoras' theorem, we can find the total speed, which comes out to be 41.4 feet per second. Okay, so we don't need to use those knowns anymore, and these are our new knowns. The x velocity, y velocity, and the speed. At point B, there's a downward acceleration due to gravity, and that can be split into a tangent and a normal component. If we compare the triangle on the right and the left, we'll see that they share the same angle, theta. Now, looking at the left triangle, we'll find that theta is the arctangent of the x velocity over the y velocity. That's just 31 degrees. Looking at the triangle on the right, we'll find that the normal acceleration is simply the magnitude of the acceleration times sine of theta, that angle. And plugging in the numbers, we'll find that to be 16.6 feet per second squared. Now back to the formulas for radius of curvature. We now have both speed and normal acceleration. We can plug them in, and we'll find that the radius of curvature is 103 feet. And now we're done. Thank you for watching.